Now we're going to talk about average velocity. And we're going to talk about it just in during an interval delta t. You'll see why, but it depends on an interval. Delta t, and just like displacements in position, delta t just means some final time tf minus some initial time ti. Okay? So let's just go for it here and define it. So what we're going to do, average velocity, we have our cursive v. We put average as a subscript when we mean the average velocity, and it's equal to the displacement delta x over that time interval delta t. So if we go back to example 2, and we have Hal here, and Hal is not rolling, he's just sliding along, we can think about this time, and plot or calculate how far did it go, the displacement along the axis delta x over the time. If we wanted to write it out a little more gory, we could even say it's x final position minus x initial position over t final position minus t initial position. Right? That's what delta x and delta t are. Or if you want to think about it sort of in words, you could say it's the displacement past xi. It's really how far you go past the initial position over the time after ti. Instead of thinking of it as an absolute final position in time, you can think of it as a continuous one if you wanted. Right? Some position past xi, some time past ti. One thing we got to keep in mind is, even though we're doing 1D, it is a vector. Even in 1D. We have to think of it as a vector. So if it's a vector, I put my vector symbol on it. And if this is a vector, somehow it has to become a vector. Oh, that's because displacement is a vector. Right? And here, what do I do here? Before we put an I hat, but here, let me blow your mind a little bit. Position is a vector. What? Position was just where it is. Position is the displacement from the origin. Right? So position is always where you are relative to some origin. You can draw a displacement vector. So positions are actually vectors as well. They're just vectors where xi is always, the origin is always 0. So that's actually what can make it a vector as well. Displacement is a vector. Okay, so now we're okay with the vector world here. Now let's look at our example of motion. This is still example 2. Okay, and here we are. We have plus t, we have plus x, and we had some offset or something, but basically for uniform motion we know it's going to be a line. So if we wanted to think about what does this v average look like on a graph like this, we need a time interval. We need ti and tf. So we don't really even care about the origin at this point. Let's just pick ti and let's just pick tf. And it cares about the values of the position when those happen. So what you can do is you can just draw a little thing up here like this and a little thing up here like this and say, where was it at ti? It was at xi. And where was it at tf? It was at xf. Okay. So there, what you can see is that, kind of like we said before, v average is the slope of that line, right? Because v average is delta x over delta t. That's rise over run, like you learned to calculate in algebra, right? So it's the slope. It equals rise over run. It equals delta x, in this case, over delta t. Okay? But now, let's look at another example of motion. So you could say all it is ever rise over run. It's over the slope. How does this ever get complicated? So here is a way it can get a little bit complicated. What we're going to do is a second example. Let me go ahead and start drawing it here. I don't have a lot of room. T, x, another xt plot. And we're going to have Hal go for a while, sort of this fast, and then speed up, and then stop. All right, so let's do that one more time. Slow Hal here, speeds up, and then stops. So we have two different velocities going. Right, so we could plot it kind of like this. You could start, doesn't even have to start at the origin. It goes at one velocity, one slope, and then it goes at a higher velocity, higher slope. like that. I'm going to be wishing I'd made that first one a little steeper. Let me draw that again. So goes 1, and then another one like that. Okay, so what we want to do now is say, what is V average for this motion? And we could define, actually, let's define 3 times. There's really 3 important times here. There's T1, there's T2, and there is T3, right? So there is no one average velocity for this motion. It really, average velocity always just depends on 2 points in time. And you can see now that things are changing, okay? So V average, let's see, I'll put a notation like this from 1 to 3, right? So the average velocity for the whole trip. It's easy to get. All you do is literally, you just read things off the graph. You say, here, at time 3, it was at x3. At time 1, it was at x1. It's just x3 minus x1 over t3 minus t1, where everything, these are all vectors, right? Keep our vector notation going. So literally, you just follow this formula. But what's interesting about average velocity is here you'll get a number, and the thing never went at that velocity, right? So Hal went some slow value of the slope here, or some slow velocity here, some high velocity here, and the average is somewhere in the middle. Right? So it never actually went the average velocity, even though it had an average velocity. Okay? But here's the other weird thing, is the average velocity is not the average of these 2 velocities. Right? So we could call this V average 1, 2 would be this slope, and we could call this V average 1, 3 would be that slope. But it's not necessarily the slope of the 2 velocities in this example. So don't let that name make you think it's an average of a bunch of numbers. It really isn't. It's just simply the final and the initial for any interval. We could calculate it from here to here, from here to here, from here to here, from here to here, from here to here. Okay? So don't let the word average trip you up. Oh, we have a question. Okay, let me see what our first question of the class is here. Andrea, plan B, why isn't time a vector? Oh, yeah. Oh, I see. I get, yeah. So here I drew this displacement, right? And I said delta x is a vector because it's a change in position. Well, why not delta t? They look exactly the same. It's t final minus t initial. So there's probably lots of really deep answers to that. But let me just give you the simple answer that sort of matters for this class. It sort of gets into why are we treating a 1D as a vector. It's always going to have a positive value or a negative value. You can just add them. There's really no need to treat it as a vector, even though the positive means one way, the negative means another way. When the vector notation becomes very powerful is when we're in 2D. Then when you add 2 things as a vector in 2D, the vector notation becomes very critical. If you just add 2 vectors in different directions, they don't just add. They have to add as vectors. Okay? So really, the simple reason is there's only 1 dimension of time, so it's not necessary. If we had 2 dimensions of time, then yeah, we'd probably have to have some weird vector time. But since we, in our simple universe, only have 1 time dimension, then we never bother to treat it as a vector. But interesting question. And now another kind of velocity, instantaneous velocity. Instantaneous velocity, we will describe that with a cursive V, but we're not going to put AVG. There's no average subscript. When you see it with just the V by itself with a vector, that means instantaneous velocity. And really, the difference is it's for very short interval delta t. And if you know your calculus, you know I mean a very short interval, like 0. Okay, so to think about this, let's start with the demo. Right? So it's the same old example 2. It's just Hal sliding along a 1D track. Uniform motion, back to the simple case. So let's go make our plot again of what that looked like. There's time plus t, there's plus x position, and it's a line, right? Uniform motion. So what is VAV? Or I'm sorry, let's go back and talk about average velocity again and see what was that equal to. Delta x over delta t. So we're going to go back to that idea. You had t initial, t final, and the way you found the average velocity is you took these up and then you went over, and we said, okay, it's kind of like the slope. Right, so you had delta x, the displacement over here, and delta t down there. So what we're going to do is conceptually, we're going to let delta t be very small. Okay? And what we're going to do then, let delta t be very small. Instead of this big delta t, let's put t initial here, and let's put t final there. Right? That goes up there. That goes up there. That goes over. And that goes over. And you can see what's going to happen. This got smaller, but this got smaller, right? They both got smaller. The ratio is going to be the same because it's uniform motion. Any two delta t's you pick, any delta t you pick, you're going to get the same average velocity, whether it's big or down here or up here or really small. So if we let it be really small, we'll get the velocity at an instant. Because we're going to get the same value no matter how small it gets. I could go here. Here's TF. Look at that. Oh, if you could only see how small that is. Zoom in. There you go. Even for that small of a delta t, we're going to get the same velocity. Right. So what this means is mathematically, let's see how we would say this. Whoops. Kali. What does this mean? Mathematically speaking, this is the derivative. So this is calculus-based physics, so we will talk about concepts from calculus, although you can kind of get by if this is the first time you're seeing them. But basically, this is the simple idea of the derivative. And what we mean is, as delta t goes to 0, as we make it really thin, then basically the V average becomes, it goes towards this thing we just call V, the V instantaneous. Just like as I was drawing here, as we shrunk down delta t towards 0, we get not the average velocity over some region, but the velocity at an instant. Instantaneous velocity. Okay? Mathematically then, we don't write the deltas. The deltas mean a big separation. When you shrink it down, we just call it d. It becomes dx dt. So that is the formula for the instantaneous velocity. It's the derivative of the position as a function of time. And it's a vector because the position, remember, is also a vector. It's the displacement from the origin. So this is our formula. If you know calculus and you're given the position as a function of time, you know what to do. Take a derivative. You know the mechanics of taking a derivative. If you don't know calculus, don't worry about it. We'll teach you a little bit about how to do it. But basically, there's a mathematical procedure to find dx dt when you know x as a function of time. Okay? Also, point out, it's still the slope. Right? It's still, what it means is it's a slope at a certain point. If you haven't had calculus, you're saying, well, then why all the complication? Why not just call it the slope? And I'll get used to it. Okay, you'll find out. Right? There'll be lots of complication. Okay. So that's instantaneous velocity. Let's now look at some more velocities. We've talked about position and displacement, but believe it or not, there's a third quantity to describe positions and changes in positions, and that is distance. So distance is how far an object actually travels. Okay? So to think about distance, we're going to do our third example, example 3, of Hal's motions. And this one is we're going to take the ramp and we're going to tilt it. And Hal is going to start at 10 centimeters. So let's say this is the origin, this is 0, and here's 10. And I'm going to push him up to 40 centimeters, maybe a little higher, but there's 40 centimeters, and he's going to go all the way back to 0. All right, so let's look at it again. He started at 10, this is 0, started at 10, went up to about 40, and then made it back down to 0. Okay, so let's plot it, draw it, do the equations, and everything. Let's see. So first, we could draw the demo real quick. So just to make sure you see what's going on, right? So in this case, here's Hal. Hal started there at 10, but this is where I caught him at 0, and he's going to make his way up to 40. And just so it's clear, even though I tilted it, now we're just making the x-axis also be tilted. Okay, so there's the origin of the x-axis, and he's moving up the tilt. Okay, no need to do trig yet. Okay, so we pushed him up, and he went up this way, and then he came back down this way. And that was the path. Right. Let's look at the graph. The kinematics plot would have time there and x there, and this is the origin. Right, and we know he started at time equals 0, he started at 10, and he's going to make his way up to 40. And it's sort of this smooth transition thing. We're getting ahead of ourselves. He was accelerating under a force. But I can kind of draw what it's going to look like. It's going to look like this. Right? He's going to start at 10, make his way up to 40, and then smoothly come down. Should be more curved than that, down to 0. But all we really care about now is thinking about the position, the displacement, and the distance. Okay? So position is plotted. We don't need to think about position too much. So this is a plot of the position. It's really little displacement vectors past the origin, but position. Let's think about the displacement. To think about displacement, we need an initial time and a final time. So we're going to say it was at t equals 0, and we'll call this t, say, as 5 seconds. Right? So we have t initial equals 0, t final equals 5. We don't even really need the times, because all we really care about is the displacement delta x equals what? X final, which was 0, 0 minus x initial, which was 10. Minus 10, we get 0 minus 10, negative 10. And since it's a vector, and I put a number, and I can't put a vector hat on a number, that'd be kind of weird, I'm going to put my I hat. It just means along the x-axis. So the displacement was negative 10. If I were to draw that displacement vector, it would look like this. There it is. The displacement from initial to final is negative 10. All this other crazy stuff happened, but it doesn't matter. Displacement just cares about initial and final. But what if we wanted the distance? All right, the distance, which we usually label d to distinguish it from position and displacement, which is x, the distance is really just how far it went. Then there's really no simple mathematical formula to get distance that I'm going to tell you about. Okay? You just have to look and say, literally, how far did Hal feel like he went? Right? So he went from 10 to 40. So that was a distance of 40. And then he turned around and went from 40. I'm sorry, he went from 10 to 40. That's a distance of 30. Right? He went 30. And then he turned around and went back to 0. He went another 40. But he turned around and went the other way, but you don't make it negative. Distance doesn't care about positive or negative. It just cares about how far you went. So he went 30 plus 40. He went 70. And if we want to do units, they're both in centimeters. So it's the same path, or it's the same trip. It's the same experiment. But you can see that the displacement was much smaller. It was small and negative, whereas the distance always positive. It's just how far it went. You can think about this in your everyday life as well. I turned on my exercise tracker and tracked myself coming here today from my house to here. Right? So now I'm showing you then the map. So there you can see my little path of all the distance I went. It's about 3 miles or so. But now here I'm also going to put on there the displacement vector. Right? So now you can see the displacement. And of course that's shorter, right? Because that doesn't have all the little turns and everything. But my car says I went the distance. But in physics I would say my displacement. I would just draw the other vector. So there you can kind of see the difference. This can be done really for any path that runs around different directions. All right, and now I'm a little concerned. My exercise tracker is telling me not to run so fast because I'm going to have a heart attack. So I should not have used my exercise tracker for that drive. But for physics education, I was willing to risk it. Okay, so that's what distance is. Now let's think about how we can use it to describe another kind of velocity.